there's a couple buzzwords that we get started with. I didn't make up any of these buzzwords, but they're buzzwords out there that you should be familiar with, and some of these you've heard, and we're going to explore these. So they are, I hate to read these to you, but we'll expand on each one: embodied energy, recycle fraction, life cycle assessment, and closing the circle. Now, closing the circle is the latest buzzword. This life cycle assessment has this delightful acronym and is actually used in product design, particularly in Europe. So it is an important thing to look at for a little while. And this is an overview. So let's look at embodied energy initially, and this is probably the most important notion I'd like you to take away from all this. And it's the notion, again, didn't make up the term, didn't make up any of this, but the notion is that when you look at a product, we'll focus on products, there's a cost for the product. You pay money for it. And that's the value that the market has assessed on the product. But within that product, there's also other costs. Some of them are social costs, like if they're made by child laborers or whatnot, or if pollution's generated for which there's no tax. So let's say you take a barge and put it in the middle of the ocean and there's no rules governing you, and you don't pay for pollution control, but some other company who is wherever does pay for pollution control. Those are called social costs. But these are, here we're looking at energy associated with actually not only making the product, but all the raw materials that go into the product. And that starts from extraction. So mining, processing, all the transportation. So from the, we'll say mine, we'll look at copper here as an example I have. So from the mine to the refinery, and then from the refinery to the dockyards, and then from the dockyards by ship up to the US and to the offloading section of Long Beach, California, onto the trains, and blah, 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 till it ends up in your smartphone as a little strand of copper wire. Okay, all that stuff. And then packaging, the energy involved with packaging things, which not only is it a marketing issue, but it's also a storage and security issue. And then storage, like for example, in business, you often assess typically like a 0.5% cost for storage, for warehousing and such. I mean, the real cost, you have to insure it, you have to heat it, you have to build a building to store things, and then administrative costs as well, or administrative energy associated with administration. And I'll give you examples of that too. I mean, and we'll look at it later, but one good example I thought was the lake source cooling system at Cornell, which I have a slide in here and we've talked about before, where there was an environmental impact assessment required. Well, that's good, that's fine. Turns out it was a lot of money for that, but with those people doing that assessment are driving their cars to work, and they're heating their offices and all these sort of things that are part of that whole embodied energy thing. So everything sort of has an impact. We're not going to go over this in detail, but you can look at this. This happens to be, if you look up here at the upper right, it says ore deposit. This is for copper. And you can see this is a diagram showing the processing for copper ore. So this is all what is used for electrical wiring, for example, and other sources. We have a lot of it on planet Earth. We're not making any more. But I was looking up the numbers. I think, well, I shouldn't quote, but there's a lot of copper left. And that's true with a lot of these minerals, but they're extractive, which means the actual material you don't pay for. I mean, it's there. You dig it out of the ground. So unlike some things, you don't actually have to make copper and other minerals and raw materials. So, but you can just kind of see from this, there's a lot of things that go on to turn the ore into wire, if you look at the bottom here. And all of these things use energy. And not only do they use energy, but many of them create a pollution of sorts, an undesired outcome of some sort, whether that is injurious to health, or it needs to be landfilled and takes up space in a landfill, whatever it is, it's undesirable byproduct. So anyway, that just kind of gives you a diagram. And this is, I put the citation here because I just wanted to show you a little bit of the numbering used for embodied energy, just to get a flavor for it. So this is a whole chart of different things, and it's these values, and don't worry at all about what the numbers mean, but some comparative things I think are helpful. So some things have a lot of embodied energy. So for example, aluminum is one of the highest, because to extract aluminum from bauxite is very energy intensive. And when you say energy, you're often talking about coal-fired plants or some kind of hydrocarbon fueled electrical generator. It could be hydroelectric, but that has issues too. It could be geothermal. It could be other sources. In fact, that's why Iceland's a popular place for making aluminum or processing aluminum, because of all the geothermal energy there. So anyway, you can see aluminum is 170, copper is 100, sort of the baseline, we'll say. Steel is much lower, and then this continues on. So what these numbers are telling you is the energy involved with making this are multiples of these numbers. So, so aluminum uses 70% more energy than copper, and this is independent of the market cost. It's independent of the market cost. So this is just an assessment of energy, okay? So just to give you an idea. Now, another buzzword, recycled fraction, and we've kind of looked at this before a bit, but it's talking about the percentage of the items that can be recycled. And there's a lot of words here, but it is an important notion in that when you're designing, well, there's two parts of it. I guess I'm cutting right to the chase in terms of designing. When you have components that can be recycled, like copper alloys and aluminum, certainly gold and silver and things like that, it's good if you can make them easily removable. So if you're trying to, if you have all these beautiful brass screws in your design, and at the end of its life, can those beautiful brass screws be extracted? Well, probably not. They're probably just going to get thrown away. But if you have some feature where all the fastening hardware is in one little spot and it can be easily removed, that's a good goal in terms of sustainable design. And economically, it's an attraction as well, especially for valuable metals. Valuable metals, like aluminum and copper, are good examples, are often recycled where steel is not, because steel isn't worth that much. So it does affect designers, and we'll look at that a little bit more in just a moment. So life cycle assessment, I have some videos on the PowerPoint you can look at about sort of give you an idea of how this is done. But again, it's that cradle-to-grave issue involved with the impact of the design. So it's actually looking at the end of the life too. What do you do with it? Do you throw it in the garbage? Do you recycle all of it? Do you recycle some of it? Do you burn it? Do you give it to somebody and it gets reused in some ways? You know, how does that all come into play? And it's done. There's a couple standards that govern this. So again, if what we're trying to do here is sort of parse market-driven cost from total embodied energy and environmental impact. And again, this isn't indoctrinational, which I talked about even before I started this. It's saying that there are some effects, and you can debate what these effects are, but there are some effects, and you're just asking the question, even though something is cheap, because it could still have high embodied energy. Okay. And then circular economy, this is looking at keeping things out of the waste stream as much as possible. So you've probably heard the mantra, reduce, reuse, recycle. So you reduce how much of something you use, you reuse things without any modifications, and then finally you recycle. That's the bottom of the barrel, because recycling requires energy and produces pollution to some degree, which we'll look at. So this is this diagram of the circular economy, and this is, you know, what happens here, and your radar should be up. You're saying, well, this sounds nice, but is it practical? Well, in many ways it's not right now, but it's sort of a goal. It's I just wanted to share with you the thought of doing, of what this is all about, but it's trying to really reduce waste and keep things in a circular fashion so that things are always reused until they disintegrate into little leptons and gluons and other such subatomic particles. So this is what I addressed before with separating materials. And if you talk about a product design, designing for sustainability is really saying that the valuable materials or dangerous materials can be separated. They can be done easily and quickly. So if it's something, if, you know, for you to extract a battery from some kid's toy, if it's going to take you more than 3 minutes, you're probably not going to do it. If it's going to require special tools, you're probably not going to do it. So when the kid's toy is all beat up and disheveled and there's, you know, 3 AA batteries in there, you might just toss the whole thing away. And that's the notion of sustainable design, is to try to make it appealing, attractive, and practical for people to disassemble things. Okay, and this is just a graph, and you can see here recycle fraction and cost, but what I'm most interested in is this y-axis, where it's talking about the things that are hardly able to recycle. Ceramics and glasses are a huge category of that, rubbers too, to some degree, but that's a really big category, whereas metals tend to be recycled often. Okay, and then this is what, again, I wish to have no indoctrinational elements at all, but there are certain things that have value, but you don't pay for. So I have water, soil, garbage disposal, maybe, and raw materials. Now, if we look at raw materials, as I mentioned, the copper is in the ground. All right, God put it there. That's where it is. And you just take it out. So the actual copper or aluminum or iron or whatever, there was no direct cost to make that. Gold, silver, all these things. All right, and the same is true for soil. Okay, soil was there. It gets depleted. You get runoff. So there's a slow, maybe degradation of soil because we don't really have river flooding systems like we used to and all that. But soil is basically free. For many people, water's free. Not for everyone, but for many people. If you have a well, but you're paying for electricity and then embodied energy, putting a well in there and all that stuff. And then disposal, well, that may be free, it may not be. It depends on your life situation. So for me, it's not free. I pay for it. When I lived in New York State, I paid a lot for it. You probably don't pay for it. If on campus, you throw something in the garbage can and you're not having to pay for disposal, even though you recognize there is a cost of disposal. But again, these things are free, but they're not free. So it gets into the debate. If you're using a lot of fresh water and you have a well and you're using fresh water for some processing operation, well, yeah, the water is free for you, but there is a value to water. And then biofuels, there's a displacement cost here too. So if you grow palm oils, if you cut down the jungle to grow palm trees and use the oil, well, that's a biofuel, which is good in a way, but then you have issues with that. And we'll look at that with combustion next class too. But you also have taken down jungle or farmland or use it for another purpose. So there's these kind of the utility costs that come into play. And then pollution and social costs I talked about before, in that if I am burning vinyl siding, which actually I had a neighbor, well, not too close a neighbor, half a mile, which was a neighbor where I used to live, he was burning his vinyl siding. Didn't cost him anything. Didn't have to landfill, didn't have to drive his vehicle to the landfill, didn't have to do anything, he just burned it. Well, I can assure you, burning vinyl siding smells really bad, and there's bad stuff with it. And same with social costs too. So those are things where you have, like I said, child labor is a good example or something like that, but there's other examples, and I'm not going to pursue that too much. Okay, this is just some little factoids on the efficiency of transport. So when your favorite movie star flies from Australia to get an environmental award, he's getting 1 mile per gallon on his G5, on his Gulfstream, okay? And I worked at a place often, we had a shortage of parts, and they were flying 747s from Japan to bring parts over on time. And there you get 1,000 feet per gallon, and then cargo ships, which are very, very efficient, as to our trains and trucks too, But of course, these numbers are just meant to poke at you. So you as a critical thinker know that you're actually looking at not just the cost per gallon or the fuel economy per gallon, but also per ton carried, per mile carried. So there's more to it. So it's not, these are unfair numbers, but they are kind of illustrative. And again, when you look at these, like if you translate 1 mile per gallon, well, there's an embodied energy. To make a G5 takes a lot of energy, aluminum and fabrication and all this stuff. You don't pull them out of the copper mines in Chile. And then to operate, it's expensive. You have these 2 pilots that run it. It's just, there's a tremendous amount of embodied energy with that. Okay. Now products, I won't belabor this because I've kind of, presented it throughout the talk here, but as a designer, you're sort of saying, from a sustainability standpoint, you're saying, can I take out the dangerous things easily? Can I take out the valuable things easily? And then you might be asking questions about, can I take everything apart easily? Can I reuse this for another purpose? And even reduce, if you look at the notion of reduction too. When you reduce weight, you save shipping costs, you save disposal costs, you do many good things. So it's very easy to over-design things, to make things too heavy and too strong, we'll say, for their use. And by doing that, you encumber the downstream side of dealing with your product, you know, the handling and the disposal. And that's one of the, you know, well, anyway, it's one of the principles of design, is to design just enough. Real quick overview of some materials, because there's a lot more. One thing I like with Zoom, I guess, you got this clock ticking pretty hard, so it keeps us efficient. And hopefully, this is like a seminar, by the way, because there's no test on this. So you can just sit back and relax and think of, if you have questions when we're done here, love to hear them. So cast iron is highly recyclable. It's heavy. It's very strong. You can cast it, and you get the oxide coating that protects it. Normally, it's gray, malleable, and ductile. They do great things, but they are heavy, which means to ship it is heavy. Copper, again, this is, many alloys come from copper, but a lot of their copper comes from Chile. So does our lithium. And to actually get to your tea kettle or to your smartphone, there's a lot of things involved, and it's actually remarkable that this all happens. Okay, then we look at aluminum, and in my world, everything would be made out of aluminum. There's very few downsides. You get this oxide coating like with copper, so it doesn't corrode. It can be very strong. It can be very beautiful. It can be very, well, it is very light. It's recyclable. There's just all kinds of good things with it. It doesn't burn. At low temperatures, it behaves nicely. But the problem is it's expensive. Okay. All right, and then plastics are made from oil. And so oil, you know, there's issues with oil too. So you're looking at crude oil, and you have a transportation system, and you have again, this isn't indoctrinational, but there is a system to protect those assets as well. Military systems, navigational systems, all this sort of thing is either, well, and that's for all transportation. I shouldn't just pick on oil, but you know, there's a infrastructure meant to protect these supply lines. So that's all part of these kind of social costs that come into play. Okay, and this is just an example. So you throw your little tiny plastic drink thing in the recyclable container, or even the single stream, which has these anyway, you know, to separate materials has embodied energy too, because especially to do aluminum and metals, you get these magnets that are pulling them out and such. Okay, but anyway, so first when you put it in the bottle, it's getting washed and chopped into flakes. Okay, so there's energy involved with that, and the flakes are dried and turned into a plastic lava, and then it's cooled and pelletized. So, you know, there's even in recycling, there's an embodied energy. Well, obviously, you know that there's a lot of embodied energy. Same with newspaper. Take newspaper, throw it into, you know, a recyclable container, good for you. Somebody's got to carry that, haul that, put it on a truck. That truck's burning. It's got a diesel engine. It's burning diesel fuel. It's creating pollution, and boom, boom, boom. Okay. Okay. Right, this is one example. I have a whole lecture about buildings I hate, which sometimes I do and sometimes I don't. This is the James Thompson building in Chicago, and I'm from that area. And this is what I'd call an anti-green building, because it's designed to be energy inefficient. So I don't want to belabor this, but commercial buildings are self-heating. The people, the computers, the lights, all that stuff heat up commercial buildings down to usually about 35 degrees Fahrenheit. They don't need any heat up down to that temperature. So generally it's a cooling problem. So you're trying to keep buildings cool. So what you don't want with cooling is big giant glass surfaces. Okay, it's great for residential, and you know, on a cold day, you know, it's all good for residential. Passive solar is wonderful. In commercial buildings, a whole different world. You want windows that do not emit light, plus the embodied energy of glass is high. And anyway, and the inside is this, it's an open structure. So it just cooks like a greenhouse, and the cooling for this is very expensive. It uses an ice storage system so it basically runs all the time, makes ice at night, and uses that ice as an adjunct to the cooling. But okay, that's a whole other thing. These are thermal solar panels. They use a little copper. I've been there. They use copper tubing. All right, little fine copper tubing that runs through here. But what I wanted to point out, Some of you, I only have 9 minutes and 14 seconds before I time out on this. I'll give you 4 seconds to tell me one problem that you see with this. 1,000, 2,000, 3,000, 4,000. Okay, good. You see shadows. So you have these expensive panels down here. Now these aren't photovoltaic, but that doesn't matter. They are sitting in the shade, which means they're not doing anything. So you have an embodied energy associated with the panels. Photovoltaics and solar thermal panels like these don't come from that mine in Chile. They're made. And this one happens to have a lot of copper in it. So they're made, there's embodied energy, you're smelting copper, you're transporting it, all this sort of stuff is going on. And then if you install it and put it in the shadow, it is not doing its job. It's bad by design. It's bad by design. And what's ironic here, you look at the workers and they're working in the shade. So, you know, now I realize the sun, you know, the shadow will move with the sun, but there's always, except for low angles, there's always some shade. And here you can see this one, you're basically at noon. You can see how the shadows are going straight down. This is south facing. So anyway, bad by design. That's what you want to avoid. Okay, we talked about this before, and this is trying to work synergistically with nature, but there is an impact here because the rejected heat. So this is a good design, but there's embodied energy with these heat exchangers. These are the low Reynolds heat exchangers we talked about, and all the materials that go into this have embodied energy. There's a real cost, so it's not like this is free. And then some would argue that the discharge, I mean, this temperature at the discharge is, I mean, energy is added to this water. So you are changing, you know, the ecosystem maybe you're not. They put a light here to keep shrimp out from getting sucked in. So this does have, you know, it has an effect and you have to look at that carefully, but there's certainly an embodied energy. However, this is a case where eliminated electric chillers. So, which the electricity comes from, you know, either nuclear or coal or natural gas. In this case, well, but I don't know what this was, but okay. And I'm going to skip this, yeah, because I want to watch my time here. Okay, and this, because I want to get into pollution. These are impacts, and this is kind of the good segue into pollution here. And I only have 6 minutes left, and we'll take a break. So, yeah, so it's embodied energy. I mean, the question is, what do you do about it? And I want to move in here to pollution, whoops. And I want to start with this term anthropogenic, which you've probably heard before. And this is pollution created by humans as opposed to volcanoes and rainforests and that sort of thing. So you have to be careful with this when you're talking. If you say chemical X is bad for the environment, well, where does chemical X come from? You can control the anthropogenic sources. In fact, there's point sources, and which are another case where of how this gets complicated. In other words, I can control a power plant's pollution. I can't control the pollution very well from your lawnmower that's 20 years old. Okay, and it's the same with natural sources versus anthropogenic sources too. So you know, anyway, I'm not going to go over this. This is a nice little guide, but I do want to go over some things here that relate to this. But I thought this was kind of a good overview, and you may agree or disagree with it. Okay, but I did want to go over buzzwords, and then air toxics. This is the first one, hazardous air pollutants. Real important issue. So you know, all your life, all my life, we've been hearing about pollution and you know, concerned about it, and we're trying to do a good job and these sort of things. Well, the EPA has a category of pollutants that are in a unique category called air toxics. And these are so bad, finger raised, they're so bad they cause birth defects and cancer. All right, they're very serious. They're known to have serious effects. So there's not really debate about it. They're bad stuff. Okay, then you have persistent organic pollutants. So these are ones that don't degrade, and then polycyclic aromatic hydrocarbons, which we'll talk a little bit more before about when we look at particulates. Okay, so air toxics. Okay, so again, what's interesting with this is, you know, sometimes like if you get in a debate with people or whatever about politics or life or whatever, it's always nice when you can agree on certain things. And air toxics, I think, are a starting point. For example, you can say, well, you know what, you can debate all this stuff and how bad it is to drink out of plastic bottles or whatever. But you know what? These air toxics, I think there's 180 of them or something like that they regulate. These kill people. Right? They cause birth defects. They're really like serious. They're known to be serious. And you can abide the scientific method, which is reproducibility. Reproducibility, which is hard to do with large systemic problems. You could say, okay, this chemical, when applied to this organism, creates this result, and I can repeat that in the lab. And that's important, again, when you have more serious conversations. We talked about, source, okay, we're talking about power plants versus lawnmowers, for example. Okay, and you can look at this on your own. I'm not going to break this down, but these are just different sources of pollution. And here's a couple, a few air toxics. You probably heard of them. That's why you don't get cadmium fasteners anymore. Mercury, chromium, and lead. So you don't have chromium, you have mercury in your thermostats and all this stuff. Okay, so you've probably heard of these as being bad. Okay, 188. All right, well, I was close. Okay, so mercury is actually, there's emissions of mercury from coal-fired plants to some degree in other sources. So, these are like real issues, and you have to make judgments. So if you say, well, all mercury is bad, well, great. But you do get mercury generated and other air toxics generated in a lot of things that you take for granted. So for example, we talk about dioxins and furans, which maybe I have here later. Dioxins and furans, all you have to do is say, well, it's the equivalent of 100 cars, and then nobody cares. So we have certain baselines. In other words, we're willing to sacrifice a certain amount of our lifestyle. And when you equate things to cars, it kind of provides a platform to compare and contrast pollutants. So if something's really generating a lot of bad stuff, you really focus on it. If it's generating a little bit of bad stuff, like for example, incinerators at hospitals, when they burn biological waste, there's bad stuff that comes out of that, but you compare it to cars, and none of it's good, but it takes kind of I think the what's the word, the zealous attack on all bad chemicals. It reduces that a little bit, I'd say. Okay, well, I am going to run out of time, so we'll all right, I can go through some of this here. Okay, so don't eat soil, all right? But kids do. We need to protect the children, right? So anyway, that's how some of this gets into people's bodies. And okay, we have the food chain that you've seen, so I don't want to belabor that. But and it was a big issue, especially when I was young, with all kinds of stuff. Not just mercury, but was it PCBs, I guess? Oh, here's dioxins and furans. All right, these are really hard to measure too, so it's hard to actually figure out what's going on. So people argue about what the source of these are, so I won't even go into that. But often these are produced in combustion processes, which we accept as our day-to-day life. Whether it's, like I said, we drive cars, we burn medicinal waste. I mean, those are things that basically we don't give up, and we want electricity. So, tough stuff. Okay, now let me get my. Okay. Anyway, there's a little debate about this. Let's see, it's 10:10, so why don't we come back at 10:30? And that'd be good. I do want to spend a few moments on particulate